Hello everyone, this is Monica Lupion and this presentation is the second part of the lecture Heat Exchanger. In the previous presentation I covered the different types of a heat exchanger, and then we started the study of the single pass heat exchanger and the first methodology that we use for the design and analysis of heat exchanger, which is called log mean temperature difference. Then we moved to a more complex geometry and we studied the cross flow and shell tube and heat exchangers. Basically, the idea is to use the same general equation as in the single pass heat exchanger, but incorporating a correction factor F. There are different charts that we can use to calculate this correction factor F depending on the geometry. You have different examples in your textbook. Basically, what we had to do is to calculate two parameters, Y and Z, depending on the capacity of the system and the temperatures at the inlet and outlet. And then using these charts, we will be able to determine the value of F and therefore be able to use the general equation. Today, I will explain the second method that we can use for the heat exchanger analysis, and it's based on the number of transfer units, NTU. This methodology was developed by Nusselt, and by now I'm pretty sure that you're familiar with this name. Nusselt was a researcher from the 20th century, and he was very active in the analysis and study of heat transfer. He, along with Smith, which was also a researcher, they developed a number of equations and a number of methodologies that are widely used even today. For the analysis of the heat transfer over equipment like in the heat exchangers, he defined this equation here. The heat rate is equal to a parameter that he defined as the effectiveness, which is the ratio of the actual heat transfer to the maximum possible heat transfer that could be transferred in ideal heat exchanger, and times the minimum capacity of the system times the difference, the temperature difference from the hot fluid at the inlet and the cold fluid at the inlet. So let's see if we can define this new parameter. The analysis of Nusselt is based on the difference of the capacity of the fluid to absorb the energy. So if we take a look to this profile, temperature profile here, it's clear that the fluids behave in a different way. This one here, the cool fluid, absorb or it's able to change the temperature profile much more stronger than this one here. The second case is the other way around. So the hot fluid is able to experiment a major change in the temperature than the cold fluid. So performing the analysis based on this capacity, the capacity is defined, as we know, as the flow rate times the thermal capacity. Performing the analysis using this parameter, this capacity of the system, we can define the efficiency of the heat exchanger as this formula here, depending whether if the cold fluid is the minimum flow fluid or if it's the hot fluid. Then you play around with the expression of the heat rate, taking into consideration a new definition. The new definition is the number of transfer units, NTU, and is defined as the overall coefficient U, the area, over the minimum capacity of the system. If you take a look to the different parameters and variables involved, you might realize that there is no temperature involved in the definition of the efficiency. Only the capacity of the heat exchanger, which is related to the flow rate and the thermal capacity. So in case that we don't know temperatures, if you remember from the previous presentation, in order to apply the log mean temperature methodology, we needed to know at least 3 of the 4 temperatures. But in this case, it seems like the dependence with the temperature is not that obvious for the calculations. So if we only know 2 temperatures out of the 4, this methodology, the NTU, is normally better than the log mean temperature methodology. I explained that if we play around with the equations and including this new definition of the NTU, we can have an equation for the calculation of the effectiveness for counter current flow and also for parallel flow. But in most of the cases, those equations are graphically represented in, these are just 2 examples that from your textbook. This is the case of the counter flow, and this is the case of a parallel flow heat exchanger. Normally, if you know the NTU, you can calculate it if you have the area, the overall coefficient, and the minimum capacity of the system. If you know NTU and you know also the ratio between the minimum capacity and the maximum capacity, you can directly get into the chart and directly make an estimation about the value of the effectiveness. So it's very easy if you know this graph, if you can get these graphs here. And once you know this effectiveness, then you can directly apply this general equation for the heat rate. This is another example also from your textbook when there is a configuration of a shell tube like the one picture in this diagram. You can have the corresponding chart that you can use for the determination of the effectiveness. 2 additional considerations that I would like to mention. One is the concept of fouling, and it's very common for equipment that after a while, after some time in operation, they started to lose effectiveness due to many different things. Like, for instance, if the fluid is corrosive, then the surface of the heat exchanger might suffer also corrosion, and that will affect to the heat transfer process in a negative manner. Those factors related to aging of the equipment are normally referred to fouling. The way we estimate this fouling factor, because as you can imagine, is very difficult because it can be due to many different conditions. But the way we normally estimate is by doing a simple analysis of, in this case, over a pipe. This is the analysis that we know. So if there is a pipe, we know that the heat rate is equal to the delta T over the sum of the thermal resistances, and depending whether if it is convection or conduction, we also know how to calculate these thermal resistances. So how can we incorporate the concept of fouling here in this equation? What we normally do is to calculate the overall coefficient U And this override coefficient also includes the resistances, the thermal resistances due to the fouling. This Ri is the fouling resistance in the inside of the pipe in this particular case, and R0 is the fouling resistance due to the external surface. So what we do basically is to incorporate these two thermal resistance here, and we can make an estimation of the fouling resistances either by taking a look to tables like this one, depending on the type of fluid, or we can also have all the different, if we know the heat rate that is being transferred, we can make an estimation of the fouling resistances. The second consideration I wanted to mention is related to the override coefficient. If you remember from previous presentation, I mentioned that this override coefficient, we assume that this is a constant value. As sometimes it's very difficult to make an estimation about that value. There are available tables like this one. This is from your textbook, when you can have a range of different override coefficient values. If you don't have any other way of calculating this override coefficient by just analytical method or using the equations that we know, these tables are very useful, at least to have an idea, to have an estimation about the override coefficient and how that override coefficient will impact the heat transfer. The second example is related to the application of the NTU methodology, and is also solved on UV-Learns. So in summary, we went through two different methodologies to design and do the analysis of a heat exchanger. The first one is the log mean temperature difference, where we apply this equation. So the heat rate is equal to the overall coefficient U times the area times delta T log mean that we define as the relationship between the delta T2 and delta T1. This methodology is very useful when we know at least 3 out of the 4 temperatures of the fluid at the inlet and at the outlet of the equipment. And what is important here is to identify what is delta T1 and delta T2. Delta T2 is the highest difference in one of the sections, either the inlet or the outlet, and delta T1 is the lowest difference in the temperature. Then we also explain the second methodology, the NTU, and in this case the heat rate is defined through the concept of effectiveness and the minimum capacity of the system. What is important here is that we only need to know 2 of the temperatures, for instance here at the inlet. So if we know only if we only know 2 temperatures, this is definitely the methodology that you can follow to calculate the heat rate. Regarding this parameter here, we defined different equations where you can directly calculate it, or you can also use charts depending on the geometry of your heat exchanger. You can use a particular chart when you calculate the parameter Y and the parameter Z depending on the temperature, and then you can directly see the value of this parameter. So if you have any questions, please send me an email or contact me on Skype. Thank you.